Okay, now, will iron sulfide precipitate out of a solution that is 0.01 molar iron and iron 2 and 0.01 molar sulfide ion on its own? So this is, we know that we have iron, it goes to iron plus 2 plus sulfide ion. So QC for this reaction would be the concentration of iron times the concentration of the sulfide, which is going to be 0.1 squared, because they're both 0.1, so this is 1.00 times 10 to the minus 4. I'm moving fast because this is applications of the many problems that we've done before along this line. Now the KSP for this reaction looks like it's 6 times 10 to the minus 18. Let me double check. Iron, yep. So QC is greater than KSP, I should say. QC is greater than KSP, so we get a precipitate. So the point of this problem is to say, well, what if instead of just having them on their own, we mix them in with a solution that contains a counter ion that can cause a complex ion to form. And if you look at all the complex ions, I mean, let's see how they list them. Yeah, they call them complex ions. They're all ions. They're all water soluble. So if this cyanide could come in and react with the iron before the sulfide could, which will happen because the KF is so gigantic, you can prevent a reaction from the precipitation from happening. So the cyanide will come along, eat up most of the iron, and then whatever iron is left can go into this QC expression, and we'll see what happens then. So what we're about to do is the problem very much like the one that we just did with the complex ions. So what we do is we have the iron. So what we're doing is we're saying that the iron is in there with the sulfide, which wants to react with it, but it's also in there with the cyanide, which has a very strong a very high KF. The KF here is 1.0 times 10 to the 35th. So even though the sulfide is in there, the cyanide, if it has a chance to react with the iron 2, will strip it away from the sulfide easily. So first we'll assume that the iron and the cyanide react completely together, just like we did before. This is 1 molar, 0, minus 0.01. And then this is minus 0.06, is that right? 0.06, yep. This is 0, and then this is 0.94 molar, and then 0.01. So we do out a problem just like we did before, and to determine how much iron is left after the cyanide gets to it, and then we're going to put the new concentration up here. And we can probably assume that it's going to make the precipitation not happen, and that's how you prevent precipitations in industrial systems where it would be easy for ions to come together. Put in a counter ion to create complex ions that will prevent precipitation from happening. So then we do the next step, which is to flip the reaction around. Remember, notice that I didn't put a return arrow here. We assume that it goes to completion. Now I should say that even this would become a 7th order polynomial, but if you are willing to sit around diligently, or you have a computer that will do it, you can solve it in the KF form. And you can even solve it with a calculator without any kind of program. And if you're interested in that, let me know. I'll show you how it's a long process of just kind of, you put in numbers to see if what works and what doesn't, and you just keep putting in sample numbers until you get the right answer, and you kind of hone in on it. And there's other approximation numerical methods you can use, but that's probably the fastest for us. Well, the fastest is to do it this way, actually. So, but the math is there. You can always do it, just in either way. But this is definitely easier because now the approximation holds, and your concentration of iron 2. Make sure that I'm on screen here. Will turn out to be 1.28 times 10 to the minus 37. I gotta believe at this point that you can take this and solve and get here. I used to do them all out, do out every step, but but not anymore. You have to, if you've made it to this point, you must be able to deal with that algebra. 0.94 to the 6th power divided by 0.01, and then solve for x. Now, the QC, this is our iron value, and we're going to put this iron value up into here, because it was 0.01 iron, 2. But when we added the cyanide, it reacted with it and brought it down to this level. And, well, actually we don't need the molars in there. This comes up to 1.28 times 10 to the minus 39. And so no precipitate. So this would be a way of, if you have a reaction and you're worried that, or you have a system where you have these ions and you're worried that they might end up reacting together, you can, if you know what you're doing, you may be able to find a way of avoiding that by putting in some ion that will cause a different reaction to occur. And, whoops, just looking at this, I'll just double check this. And so I get 9.4 to the 6th divided by 0.01. And I get, this is 1.45 is what I'm getting this next time around. So the 1.45. And so this would be 1.45 times 10. It doesn't make any difference as far as the ultimate answer. Let me try it one more time. Something seemed off there when I was looking at it, and now I'm going back. And everything is fine otherwise. So we have that number, and then we take, then we divide by both sides. Okay, yeah, so 1.45. So sorry about that. It's different than I have on here, but it looks good. So looks like that should be the right answer. But still, no precipitate. Not too worried, because it's still a fantastically small number. Okay, now I did the same thing here where I did out the problem. So since I already did it out, same kind of thing. Will silver chromate precipitate out? Here's silver chromate. Now it's a 2 to 1. That's why I have it in here. I have something a little different. 2 to 1 for the cation versus the anion. Went 0.1 molar silver and 0.1 molar chromate. If we put those values in, here we see that it's much larger than our KSP, so there should be a precipitate. However, if we have this thiosulfate ion present, then the silver, 0.1, and the thiosulfate is 2 molar. Then we do out the problem as normal to determine the amount of silver that's left over. We flip the reaction around, and then we solve for the silver ion. We end up with 1.06 times 10 to the minus 15. And so instead of having 0.1 molar that goes up here, and we do the calculation down here, we end up with a very small number, no precipitate. So by adding that counter ion, that thiosulfate, we can actually take care of, or keep it from precipitating out, or keep silver from precipitating out. So that is that.